Hello, everybody. I'm glad you could join me on our pavement materials and design journey. In our last lecture, we have learned the asphalt mix design. Today, let's learn about the structural design of flexible pavement. The flexible pavement design will take 2 lectures to cover the content, and this lecture mainly focuses on its first part. Since we have learned different pavement materials, the aggregate, the cement, the concrete mix design, the asphalt and asphalt mix design, it's time for us to combine them to design a pavement. Because of many variables and interactions which influence the result, it is appropriate to adopt a systematic method to design the pavement. The system for the design of pavement is shown in this flowchart. Although in a practical design procedure, some parts of this system may be omitted or combined with others, it is convenient to use this figure to demonstrate the relationships between the input variables and the analysis methods and the decision process which comprise pavement design. This lecture will focus on the project reliability, the construction and maintenance considerations, the environment, subgrade evaluation, and pavement materials. So the left circle, they are the input variables in the pavement design system. The next lecture will focus on the design traffic and structural design of flexible pavement. Once the design is completed, it could be implemented, and the feedback will be used to refine the design procedure. In the previous lecture, we have learned the structure of flexible and rigid pavement. For flexible pavement, it is composed of bearing surface, the base, subbase, and subgrade. While for rigid pavement, it is composed of cement concrete, subbase, and subgrade. The interface between the subbase and subgrade is the design subgrade level, the DSL. Normally, the pavement is a layered system, and the base and subbase may contain multiple bond or unbound layers. The bond layer is to mix the base or subbase material with binder, for example, the cement, to get better strength of that layer. The subgrade is the native material beneath the pavement. Here is the comparison between flexible and rigid pavement. Please pay more attention on the text in red color, as they are relatively more important characteristics of both pavements. We could rely on these characteristics to choose the type of pavement. Most highways in the world use flexible pavement due to its low completion cost and shorter time to repair. The aim of the pavement design is to select the most economical pavement thickness and composition, which will provide a satisfactory level of service for the anticipated traffic. In this pavement design system, the external factors are the project reliability, construction, and maintenance consideration, and environment. These factors affect the desired material performance. So let's go through them first. Then we will get to know the subgrade evaluation and pavement materials. An integral part of the pavement design process is an assessment of how well the outcome of the design, the constructed pavement will perform. Because of the lack of uncertainty, there are variations in the thickness, and the qualities of materials can vary from day to day. So the designer needs to allow for this uncertainty and variation in the performance prediction. An appropriate measure of the anticipated performance of the proposed pavement is project reliability. The project reliability is the probability that the pavement will outlast its design traffic before major rehabilitation. Normally, the road agency or designer chooses the designed project reliability. So typical project reliability levels are given in this table below. The project reliability is selected based on the class of the road, either is freeway, highway, or other type of road. Here, the AADT means the annual average daily traffic. It is the total traffic volume on a highway or road for a year divided by 365 days. AADT is a useful and simple measurement of how busy a road is. Here in the table, the freeway you might design for reliability of 95%. If you choose that, it means 95 out of 100 constructed pavements of that design will outlast the design traffic. So there's only a 5% chance that the pavement will be distressed within the design period. And you can see the reliability levels that people use are often related to the importance of the road you prepare to take up a little more risk for lightly trafficked road compared with a heavily trafficked road, where the consequences of early distress result in significant road user cost to rehabilitate the pavement. We can see that the larger the AADT, the higher the project reliability from this table 2.1. The design procedure is based on the structural analysis of multi-layer pavement subject to normal traffic loading. The critical locations of the strands within a flexible pavement model and the idealized loading situation are shown in the in this figure 8.2. The pavement materials are considered to be homogeneous, elastic, and isotropic, except for unbound granular materials and subgrade, which are considered to be anisotropic. The response to load is calculated using linear elastic model, such as that contained in the computer program Circly. You will have more practice in your Lab 2 session. In the flexible pavement, the bond materials are made asphalt and cement, and they have the tensile strength. Here we can see that for flexible pavement, there are 3 critical locations: the tensile strength at the bottom of asphalt, the tensile strength at the bottom of cemented materials, and the compressive strength at the top of subgrade. Because that's where the cracking starts. So during design of the flexible pavement, we have to check these 3 locations and make sure the design value is acceptable. There are 3 damage models in these 3 critical locations: the asphalt fatigue, cemented material fatigue, and subgrade rotting, and the loss of surface shape. This formula is the fatigue relationship for cemented material, and it can be used to give an indication of fatigue life. The fatigue is the weakening of a material caused by cyclic loading that results in progressive and localized structural damage and the growth of cracks. This relationship generally has been found to be in accordance with observed performance. In the formula, the N is the allowable number of load repetitions. E is the modulus of cemented material in megapascal. The mu epsilon is the load-induced tensile strength at the base of cemented material. The RF is the reliability factor for cemented material fatigue, which can be referred from the table. We are having a design process allowing for the variability in performance between projects. So not all projects will perform the same. So we need to allow for that variability in our predictions of how long pavements will last. And we do that through the inclusion of reliability factors. When there's a higher project reliability requirement due to the class of the road, such as freeway, there's a smaller RF value, and correspondingly, the N value will be smaller as well. In other words, increasing project reliability will decrease allowable number of road repetitions. The predicted profiles of allowable load repetitions versus the microstrain mu epsilon for project reliability from 80% to 97.5% are shown in the figure below. In the above formula, the Young's modulus is provided as 2000 megapascal. So the only variable is the microstrain. We can see that for the same microstrain, the allowable number of load repetitions N increases with the decrease of the project reliability. So let's say for the same microstrain 100, so project reliability from the blue curve to the red curve gradually decrease. But then when we read from the vertical axis, the N actually increases. And you can see in this graph here, the significant effect the reliability factor can have on the predicted life for a given strain. So the choice of reliability level for the project has a significant effect on the life that you calculated. Similar as the cemented material fatigue model, here is the formula for the asphalt fatigue model. Most parameters are similar as the cemented material fatigue model, where the only difference is the parameter, the VB here. So which is the percentage by volume of bitumen in asphalt. We learned this parameter in lecture 6, and it is the effective volume of bitumen excluding the absorbed binder. Also for the same E, VB, and microstrain, we can see from this figure that the allowable load repetitions, the N, increases with the decrease of the project reliability. So same conclusions can be found both for the cemented material fatigue model and asphalt fatigue model. After we discussed project reliability, next is the construction and maintenance considerations. The type of pavement structure could be affected by the construction and maintenance policies. Since construction also affects the property and performance of materials, considerations need to be taken during the construction include the compaction level, curing, concrete, or cemented materials, the type of equipment, and subsurface and surface drainage. For example, we need to make sure the pavement selected is compatible with the available equipment for construction. The environmental factors which significantly affect pavement performance are moisture and temperature. The modulus or strength of unbound materials and subgrains are heavily dependent on the moisture content of the materials. For expensive subgrade soils, the moisture changes in these materials can lead to volume change and affect the rate of the surface. There might have moisture infiltration the surface, or it might be coming through infiltrating the shoulders and then into the pavement. It could be coming from the water table underneath. So there are many factors that are affecting the operating moisture content and that need to be considered when the designer is selecting the subgrade strengths to use in the design. Temperature environment also has a major influence on the performance of pavement. For asphalt surfaced pavement, the asphalt becomes stiff and relatively brittle at low temperatures when it is susceptible to fatigue cracking. But it is soft and viscoelastic at higher temperatures when it is susceptible to permanent deformation. Temperature may also affect the properties and performance of cemented layers and concrete. It could also have a significant effect on the rate of strength gain of these materials. And if high temperatures occur during construction, drain out will result impairing both the ultimate strength and fatigue characteristics of the materials. In previous slide, we have discussed the project reliability, the construction and maintenance considerations, and environment factor. Now, let's look at the details of the materials section, including the subgrade evaluation and pavement materials. For the materials, we have to check the damage indicators at the critical locations. In other words, the vertical strand at the top of the subgrade, the tensile strand at the base of the asphalt, and tensile strand at the base of cemented materials. For these materials and at critical locations, there are three corresponding material damage models: the asphalt fatigue, the cemented material fatigue, and subgrade rotting and loss of surface shape. This subgrade strength criterion is to limit permanent deformation of unbound granular materials and subgrade from an estimate of the subgrade strength. Just keep in mind that we are talking about here is the strength in the pavement that relates to the deformation of the surface and the allowable loading in terms of the surface deformation. Among these formulas, the N is an allowable number of load repetitions before materials fails. We also learned the physical meaning of other parameters in previous slide, so I won't elaborate further here. We also have to decide and choose material properties. The materials are assumed to have elastic properties. The bond materials, the asphalt and cement, are considered isotropic, while unbound materials and subgrade are considered anisotropic. Isotropic means the properties in the X and Y direction are the same. So obviously, anisotropic means the properties in the X and Y direction are different. While homogeneous means the property is the same for any direction or anywhere within the material. The isotropic materials are normally defined by 5 elastic constants. The Young's moduli EH and EV, the Poisson's ratio μH and μV, and shear modulus. The isotropic materials are defined by 2 elastic constants, the Young's modulus and Poisson's ratio. This is because for isotropic materials, the properties in the X direction and Y direction are the same, and V direction are the same. So we only need to use one symbol to represent it. Why there's no shear modulus here? Because for isotropic material, the shear modulus could be expressed by the other two parameters. So G has a relationship of and could be with E and mu and could be expressed by them. This table summarizes the characteristics of the previous various categories of pavement materials. From this table, we can find the materials type, the behavior characteristics, the distress modes, the input parameters for design, and some performance criteria for different pavement materials. From unbound granular materials in the left to the concrete in the right, the tensile strength gradually increases. The granular materials are not linear elastic, and the modulus depends on the stress level and stiffness of nearby layers. For such case, the sublayering is recommended by the authors. In the mechanistic design procedure, normally the vertical modulus of unbound granular materials, including the subgrade, is taken as twice the horizontal modulus, as shown in the relationship here. So the ratio of EV and EH is 2. For the treatment of granular materials, there are 2 scenarios. For granular materials placed directly onto a bond cemented subbase, as shown in this figure, no sublayering is required, and it is considered as homogeneous layer. If we look at the second scenario, for granular materials placed directly on subgrade with no cemented subbase, then sublayering is required. According to authors, it is advised to divide the total thickness of the unbound granular materials into 5 equal thick sublayers. So for dealing with such sublayering case, we normally follow the following 3 steps. Firstly, we divide the total granular layer thickness into 5 layers of equal thickness, as discussed in the previous slide. Then we determine the vertical modulus of the top sublayer. It is the minimum of the suggested values in table. So it's the minimum value of the value suggested in table 6.4 and 6.5, which I will show you later on, and that determined using this formula. The EV underlying material is the vertical modulus of the subgrade. So finally, the ratio of the adjacent sublayer is given by the following equation here. If we know the capital R, then we are able to work out the vertical modulus accordingly. So the software certainly automates many requirements of the author's procedure, such as this sublayering of unbound granular layers. Now let's look at one example. So in this pavement structure, the granular material is in direct contact with the subgrade, so sublayering is needed. We need to firstly work out the vertical modulus of the subgrade. The California bearing ratio CBR provides an indicator or index of the shear strength. Here we have CBR of 5 for subgrade. The unbound granular material has thickness of 475 millimeter. The vertical modulus of a subgrade can be determined from laboratory testing of conditioned samples or by using the empirical relationship as shown here. So EV equals to 10 times the CBR. Now the modulus for the subgrade is is 50 megapascal, and the modulus for the top layer of the unbound granular material is given as 400 megapascal. So now let's calculate the vertical modulus for the other 4 sublayers. The ratio R could be calculated using this formula, and we get the value of 1.585. Then the modulus for the other sublayers could be calculated accordingly. For example, the modulus for the second sublayer is 400 divided by 1.585 equal to 315 megapascal. So in this way, we are able to get the vertical modulus for each sublayer. For the subgrade evaluation to get CBR value, we have 3 methods: the lab testing, the field measurement, and empirical values. The CBR test measures the force required to push a plunger of a specified cross-sectional area into a prepared surface of the sample material. The California bearing ratio is expressed as P divided by PS times 100, where the P is the measured pressure on site soil or the soil sample in this testing container, and PS is the pressure to achieve equal penetration on standard soil or crushed rock. The CBR is 100% for crushed California limestone. And also, the CBR is usually calculated for penetration of 2.5 millimeter and 5 millimeter. This figure contains example CBR testing results. So in this figure, the top curve, this one, is the curve for standard soil or crushed rock, for which the CBR is 100%. The below one is the curve of the lab testing on site sample. So we find from the horizontal axis the penetration of 2.5 millimeter and 5 millimeter, and then take the corresponding load reading from the vertical axis. So finally, we work out the ratio of load on testing sample and the standard sample, the DE over DF and AB over AC. Because the sample area is the same, so the ratio of load is also equivalent to the ratio of pressure. The CBR value is whichever is the greater for the ratio at 2.5 millimeter and 5 millimeter, corresponding to 63% or 67%. So finally, the CBR value of this material is taken as 67%, because that's the higher value amongst those two results. For the subgrade CBR evaluation, the second method is the field measurement of CBR. The in situ CBR test involves driving a cylindrical plunger of a predefined area into the soil at a uniform rate. This requires the use of a reaction load, for example, a four-wheel drive vehicle or mechanical excavator to provide the force. Alternatively, a profile of equivalent in situ CBR can be measured using the dynamic cone penetrometer. It is normally used to determine underlying soil strength by measuring the penetration of the device into the soil after each hammer blow. The CBR can be determined from the result of the dynamic cone penetrometer test in this figure. This is a general relationship that suits most fine-grained cohesive soil types. We can see that the higher the penetration, the lower the in situ CBR, and the softer the soil. The third method is the adoption of presumptive subgrade CBR values. Typical presumptive values of CBR are given in this table. They are based on a lot of experience and lots of lab testing. Designers have used them according to the material type and the materials classification, whether the subgrade is a highly plastic clay or silty clay, sandy silt, or sand. So if the subgrade is composed of sand with excellent to good drainage or fair to poor drainage, the CBR is recommended to be taken in between 10 to 18. If you are not able to conduct either the lab testing or field testing, then you may be able to refer to the empirical values in this table with account of local experience. After talking about the subgrade, let's look at the unbound granular materials. There are two methods to measure the modulus of the unbound granular materials: the direct measurement method and the presumptive values method. In direct measurement method, the modulus is measured in a triaxial cell and repetitive loading conditions. Normally, the modulus of elasticity is the stress divided by strain or slowly applied load. The resilient modulus is stress divided by strain or rapidly applied loads, like those experienced by Pavement. So in this stress strain curve, the recoverable part of the actual deformation response, in other words, the gradient of the recoverable stress strain curve is the resilient modulus, MR. The second method, or the presumptive value method, is to refer to empirical tables. This table includes values for base quality materials, high standard crushed rock, and normal standard crushed rock, and base quality gravel, and sub-base quality materials. Normal standard crushed rocks are those commonly used by road authorities. Because the moduli of unbound granular materials are stress dependent and dependent on moisture and compaction levels in the road bed, caution must be exercised in applying this empirical data. This table may be used as a guide when assigning maximum value to granular materials and seeing bituminous surfacings when other more reliable information is unreliable. The unbound granular materials are the anisotropic materials, and the anisotropy is the ratio of vertical modulus and horizontal modulus, which is 2. So if you know the vertical modulus of the unbound granular materials, you can easily work out the corresponding horizontal modulus. The presumptive vertical modulus of top sublayer of normal standard base material under asphalt surfacing or cemented material can be seen from this table. This table 6.4 and 6.5 in the next slide could be used as a guide when assigning maximum vertical modulus value to base quality crushed rock materials and asphalt surfacings when other more reliable information is available. The first column in the table is the thickness of overlying bond material, and second row is the modulus of overlying bond material. If the thickness of the overlying bond material is 75 millimeter and the modulus of overlying bond material is 2000 megapascal, then the vertical modulus of top sublayer of normal standard base material is 350 megapascal. Normally, the maximum moduli used for subbase should not exceed that for normal standard base as indicated in this table. As you can see here, how the modulus reduces. So they reduces with the depth, with the increase of the depth, because the stress is varying with depth. So this is a workaround for use in our linear elastic model to overcome the deficiencies of not allowing for the stress dependency of individual layers in terms of the granular modulus. This table contains the suggested vertical modulus of top sublayer of high standard base material. If we know the thickness of the overlying bond material, for example, 100 millimeter, and modulus of overlying bond material, for example, 3000 megapascal. And then the vertical modulus of top sublayer of high standard base material is 410 megapascal. Now let's go back to look at the previous example. According to previous formula, equation 21, the EV is calculated as 696 megapascal, while assuming high standard crushed rock as granular material with 40 millimeter overlying bond material, and referring to table 6.5. This table is 40, and no matter the modulus of the overlying bond materials, we can see the vertical modulus of top sublayer of high standard base material. They are all 500 megapascal. So that's how we pick up the value here. So the EV for this unbound granular material is the minimum of those two values. So it is 400 megapascal. Another important pavement material is cement, which is considered to be isotropic with tensile strength. In the normal operating condition of the pavement, its elastic response is normally regarded as linear with an elastic modulus and Poisson's ratio. The Poisson's ratio is shown to have relatively little influence on pavement thickness requirements within the normal range. Commonly, it is assumed to be 0.2. There are mainly two methods to determine the design modulus of cement: the laboratory tests and empirical values in the design table. The laboratory test includes the flexural test, direct tension test, longitudinal vibration test, indirect tensile test, and direct compression test. The setup of the 3-point flexural loading test is shown here in the bottom figure. The sample is supported by two supporting pins, and there's a loading pin to apply the force. This 3-point loading of sample with a span over depth ratio greater than 3 is favored for modulus characterization, as the test conditions are considered to simulate the strain gradients generated within a pavement layer. The presumptive values of elastic characterization of cemented materials, including design modulus, could be found from table 6.7. The modulus values presented in this table may be used as a guide if no other more reliable information is available. The moduli of cemented materials are dependent on a number of factors, such as the material quality, the binder content, and density. The presumptive values can't account for variations in these important parameters, so it should be treated with caution. Previously, we have covered the pavement materials from bottom to top, including the subgrade, unbound granular materials, and cemented materials. The last important pavement material is asphalt. The resilient modulus of the asphalt could be measured using the standard indirect tensile test IGT, adjusted to the weighted mean annual pavement temperature WMAPT and the rate of loading in the roadbed. This is because the asphalt modulus is sensitive to temperature and rate of loading. The higher the temperature, the lower the modulus. The higher the loading rate, the higher the modulus. So the temperature environment of asphalt must be taken into account in pavement design and analysis. Table 6.413 presents modulus values from indirect tensile test and the standard test conditions for typical dense graded asphalt mix used by Austral's member authorities. The results are for laboratory manufactured samples with the likely range of values together with typical recommended values. These values are provided for a range of mix size and binder type. For example, for binder class C320 and mix size of 14, the typical modulus of dense gradient asphalt is 5,000 megapascal. The second method is estimating the modulus from the bitumen properties and mix volumetrics using shell normal graph in combination with the in-service temperature WMAPT and rate of loading in the roadbed. This method is developed by Shell to obtain reasonable estimates of modulus of mix, which include conventional bituminous binders. The Shell method has two stages. Firstly, the modulus of bituminous binder is determined for specific bitumen in the specific pavement design situation. For example, the traffic road, traffic speed, and operating temperature. Then asphalt modulus is determined from the bitumen modulus and the volumetric composition of the mix. Now let's look at one example. The normal graphs produced by Shell to undertake these above two steps are reproduced as figure 6.9 and figure 6.10. In determining the asphalt design modulus, you need to consider what your in-service temperature would be for your project and also your rate of loading. The time of loading is 1 divided by V. Where this V as with the unit of kilometer per hour is the design heavy vehicle speed. The operating temperature is equal to the effective temperature of asphalt WMAPT, and T800 PEN is the temperature at which the penetration of bitumen is 800 or 0.1 millimeter. Finally, the PI is the penetration in index of bitumen measuring temperature susceptibility. So for this example, the operating conditions are temperature equal to 27 degrees, and loading time is 0.02 seconds. T800 PN is 58 degree, and pi is negative 0.5. So firstly, we need to connect 0.02 seconds on the time scale with temperature difference 58 minus 27 equal to 31 degree. So we found read 31 here and connect 0.02 to 31. And then we extend the dashed line to intersect with the lines of stiffness modulus with pi of negative 0.5. So it's here, negative 0.5 here. Then we read from the value in the horizontal axis. We can see that the stiffness of the bitumen determined from this normal graph is SB equal to 20 megapascal. So that's the first step. After we get the stiff modulus of the bituminous binder, for this case is 20 megapascal. Next, we go to the figure 6.10. So we label SB here, 20 here. So, and if we know the effective volume of binder, which is VB equal to 11%, and also the volume of mineral aggregate, VG, that's 82%. We can refer to the figure 6.10. So we just draw a horizontal line through this 20 and find the VB equal to 11% roughly here. Then we just draw a vertical line and intersect with VR, the line with VG of 82%. So 80 is here, 85 here. So 82 somewhere in between, or roughly in the middle. And then we just draw the final horizontal line intersect with the vertical axis. And if we take the reading, so we can find the stiffness modulus of the bituminous mix is roughly 3000 megapascal. You have learned the red diagram from our last lecture and corresponding mathematical expressions and physical meaning of each parameter. So in this example, we have used the VB and VG here. So I won't just go into more details for now, but just I put it here for your reference. A summary of this lecture: we have briefly reviewed the multi-layered structure of flexible and rigid pavement and their differences. The factors influencing the material performance, including the project reliability, the construction and maintenance, and the environment, are discussed. We also learned the damage models for asphalt, the cemented materials, and subgrade. The measured and presumptive properties for subgrade and pavement materials are discussed. We also learned the sublayering of unbound granular materials and the calculation of the vertical modulus. Finally, the shell method for determining asphalt modulus is discussed and practiced. That's all I have for this lecture, and I appreciate your attention. In next lecture, we will continue to learn the structural design of flexible pavement. Thank you and have a great day.